China didn't just build bridges that cross water. They built bridges that defy everything engineers thought was possible over water. One of them stretches 34 miles across open ocean. That's 20 Golden Gate bridges, laid end to end, over one of the busiest shipping lanes on the planet. You heard that right. 20 Golden Gate bridges. And the steel it took to build it? Enough to construct nearly 60 Eiffel Towers. But that megastructure is only the final stop. Before we get there, you're going to see floating highways that ride the surface of rivers, bridges that survive the largest tidal bore on Earth, and roads built over water so deep that foundations had to be reinvented from scratch. And it starts with a bridge that doesn't even touch the bottom. The engineering challenge: why water changes everything. Before we get to the countdown, you need to understand something. Because when you picture a bridge, you're probably thinking concrete pillars, steel beams, and a road on top. Simple enough. But the moment you move that bridge from dry land to open water, every single rule you thought you knew breaks down. Start with what's beneath you. On land, you drill down until you hit rock, and you build from there. Over water, that rock might be 100, 200 feet below the surface, buried under layers of soft silt and clay that can barely hold their own weight, let alone a 6-lane highway. But unstable ground is only the first problem. The water itself never stops attacking. Currents push sideways against every pylon, every hour of every day. Waves hammer the structure in cycles, slowly fatiguing the materials in ways that land bridges never have to deal with. And if you're building in salt water, corrosion starts eating your steel and concrete from the moment the first pylon goes in. Then comes what's above the surface. Wind loads over open ocean are brutal. There are no trees to break the gusts, no hills, no buildings. Just miles of flat, open fetch where wind builds speed and hits your bridge with everything it has. And in southern China, that wind sometimes comes in the form of a typhoon with gusts that can top 125 miles per hour. And here's the part most people never think about. If your bridge crosses a shipping lane, you can't just line up pylons across the water like fence posts. Massive container ships need to pass underneath. That means you have to engineer enormous gaps in your structure spans of 500, even 1,000 feet, with no support columns at all, and the road above still has to hold. So how do you solve all of that at once? Chinese engineers developed a toolkit that sounds almost impossible. Floating pontoons that ride on the surface. Deep water pylons hammered into the seabed. Cable-stayed systems that leap across vast distances between towers. Prefabricated sections built on land, floated out on barges, and lifted into place by massive cranes. And in the most extreme case, immersed tube tunnels, prefabricated sections sunk to the ocean floor and joined together underwater. Every bridge on this countdown uses a different combination of those tools. And every single one was built where most engineers would have said building was impossible. The first one doesn't even try to reach the bottom. Bridge #6 Yongjiang Floating Bridge. Every other bridge on this list fights the water. This one gave up fighting, and that's exactly what makes it brilliant. The Yongjiang Floating Bridge doesn't sit on pylons. It doesn't rest on foundations drilled into the riverbed. It floats. The entire road surface sits on top of hollow, watertight pontoon sections that ride the water's surface, rising and falling with the river like a dock at a marina. Except this dock carries cars. Now, if that sounds like something that shouldn't work, you're not alone. The idea of driving your car across a bridge that's literally bobbing on a river goes against every instinct you have about what a road should be. But the engineering behind it is far more calculated than it looks. The bridge is built from 26 individual pontoon sections, each one connected to the next through a precision locking system. The pontoons themselves are steel, but they're not hollow shells just hoping to stay afloat. They're filled with dense, buoyant foam, so that even if the outer hull were damaged, the bridge wouldn't sink. Each section is anchored to the riverbed with heavy cables that keep the whole structure from drifting downstream, while still allowing it to flex and shift with the current. That flex is the key. A rigid structure fighting a moving river would eventually crack and fail. But this bridge bends with the water. It absorbs the energy instead of resisting it. But here's where it gets tricky. There's a strict speed limit for vehicles crossing the bridge. Not because the road surface can't handle the weight, but because a car moving too fast creates waves. And waves on a floating bridge are the last thing you want. Drive slowly, and the surface beneath you barely moves. You feel a gentle sway, almost like being on a boat. Push the speed too high, and that sway becomes a violent rocking motion that can destabilize the entire span. In 2023, a vehicle ignored the limits, caused the bridge to sway violently, crashed through the railing, and plunged into the river. 5 people didn't make it out. So why build a floating bridge at all? Why not just sink pylons into the riverbed like a conventional crossing? Because sometimes the river won't let you. The Yongjiang's depth, current speed, and the geology of its riverbed made traditional pile-driven foundations either wildly impractical or prohibitively expensive. Rather than spending years and billions trying to anchor something to the bottom of a river that didn't want to cooperate, engineers chose the more elegant solution. They stopped fighting the water and started floating on it. It's a fundamentally different philosophy of bridge building. And it works. Every day, you can watch vehicles cross the Yongjiang on a road that has no foundations, no fixed supports, and no connection to solid ground beneath it. Just steel, foam, cables, and the river itself holding everything up. But floating on water is one thing. Building across a lake that can't decide how deep it wants to be? That's a completely different nightmare. Bridge. #5 Poyang Lake Bridge. Imagine you're an engineer, and someone hands you a site survey for a bridge. You look at the water depth readings and notice something strange. The numbers don't match. In the wet season, the water is 40 feet deep. In the dry season, that same spot might be ankle-deep mud. The lake you're supposed to build across can't even decide if it wants to be a lake. Welcome to Poyang, China's largest freshwater lake and one of the most unpredictable bodies of water on the planet. Its surface area swells to nearly 1,400 square miles during the monsoon, then shrinks to a fraction of that in the dry months. Water levels can swing by more than 30 feet between seasons. Locals have an old saying about it. It's a lake in the wet season, but a river in the dry. And that wildly unstable environment is exactly where China decided to build a nearly 3.5-mile cable-stayed bridge. But the shifting water levels weren't even the scariest part. The Poyang Lake No. 2 Bridge sits in a stretch of water that locals have nicknamed the Bermuda Triangle of China, a zone around the Laoye Temple area that has swallowed boats and ships for centuries. The water here is deceptive. Conditions change fast, currents shift without warning, and the hydrological profile of the lake beneath you can transform completely from one month to the next. So how do you anchor a bridge in a lakebed that's basically shape-shifting? You can't design your foundations for wet season depths and ignore the dry season. You can't build for calm water and hope the monsoon currents don't rip everything sideways. Your pylons have to function in what amounts to 2 completely different environments depending on the time of year, submerged under 30 feet of turbulent lake water in the summer, then exposed to open air and dried out sediment in the winter. The engineering team solved this by driving foundations deep far below the fluctuation zone into stable layers of the lakebed that don't care what the surface is doing. The main span stretches nearly 1,400 feet, supported by cable-stayed towers designed to handle wildly different wind and wave profiles as water levels rise and fall around them. But the construction itself might have been the hardest part. You can't build a bridge this size by sending workers out over open water in small boats and hoping for good weather. So the team went modular. Massive sections of the bridge were prefabricated on land and in shipyards, loaded onto barges, floated into position on the lake, and lifted into place by enormous floating cranes. That approach kept workers safer, allowed for factory-level quality control, and dramatically cut down the time crews had to spend over unpredictable water. And through all of it, the team had one more constraint that had nothing to do with engineering. Poyang Lake is home to the critically endangered Yangtze finless porpoise, a species as rare as the giant panda. The construction zone sat inside 2 national nature reserves. Every pylon placement, every barge route, every piece of heavy machinery had to be planned around protecting an ecosystem that couldn't afford a single mistake. 38 months after construction began, the bridge was finished. And today, it sits over one of the most volatile lake environments in China. a structure built to survive in a place that refuses to stay the same from one season to the next. But surviving a moody lake is one thing. What happens when you try to build a highway across open ocean for the first time in your country's history? Bridge. #4 Donghai Bridge. Everything you've seen so far, the floating pontoons, the lake crossing, was a warm-up. Because with the Donghai Bridge, China stepped off the edge of the continent and started building into the open sea. Before 2005, China had never built a major bridge across open ocean. Rivers, yes. Lakes, sure. But the actual sea, with its deep tidal currents, massive waves, and typhoon-force winds, was uncharted territory. And the location they picked for their first attempt wasn't some sheltered bay. It was the East China Sea. The Donghai Bridge runs 20 miles from Shanghai's Pudong district straight out into open water, connecting the mainland to the Yangshan deepwater port. When it was finished, it was the longest sea-crossing bridge on the planet. And you need to understand what building 20 miles of highway over open ocean actually means, because it's not just a longer version of a river bridge. It's a fundamentally different beast. Out here, there's nothing protecting you. No shoreline breaking the waves. No headlands shielding the structure from wind. The sea hits the bridge from every direction, all the time. The maximum wave height in this zone can reach over 40 feet during storm season, and the construction window? Only about 180 days a year. The rest of the time, conditions are simply too violent to work in. But the engineers couldn't wait for perfect weather. They had to build through it. To drive foundations into the seabed, they sank more than 5,000 steel pipe piles into the ocean floor using hydraulic platforms that could elevate themselves above the waves. Positioning had to be exact. They used real-time GPS systems to achieve accuracy down to the inch, even while tidal currents tried to drag everything sideways. And then, there's the shape of the bridge itself. If you look at the Donghai from above, it doesn't run in a straight line. It curves a long, sweeping shape across the water. That wasn't an aesthetic choice. A straight bridge spanning 20 miles of open sea would act like a wall against crosswinds, creating dangerous turbulence for drivers. The S-curve breaks up the wind profile, reduces lateral loading on the structure, and helps prevent driver fatigue on a crossing that takes over 20 minutes at highway speed. The main navigation span uses a cable-stayed design with a central gap of nearly 1,400 feet wide, enough for 10,000-ton cargo ships to pass underneath on their way to Yangshan Port. The towers supporting those cables rise over 340 feet above the waterline. And every single piece of this bridge is under constant attack from salt. Salt water corrodes steel. Salt spray eats concrete. The ocean doesn't stop. Engineers use specially formulated high-density concrete and anti-corrosion coatings designed to fight deterioration for a projected lifespan of 100 years. The first bridge in China designed with that kind of service life. The whole project took just 40 months. 40 months to build a 20-mile highway across open ocean in a country that had never done it before. But China wasn't done with the sea. The next bridge would be built in what its own engineers called the most complicated ocean environment on Earth. Bridge #3, Hangzhou Bay Bridge. If the Donghai Bridge was China's first step into the open sea, the Hangzhou Bay Bridge was the moment they decided to pick a fight with it. Hangzhou Bay sits where the Qiantang River meets the East China Sea, and it is, by almost every measure, one of the worst places on the planet to build anything. The bay is home to one of the 3 largest tidal bores on Earth. If you've never seen one, picture this: a wall of water up to 30 feet tall, moving upstream at 25 miles per hour, slamming into everything in its path. That's not a once-in-a-century event. That happens regularly, and it happens right where this bridge was built. But the tidal bore was only the beginning of the nightmare. The seabed beneath Hangzhou Bay isn't rock. It's soft, silt, and clay, the kind of ground that shifts and compresses under load. Typhoons rip through the region every summer, throwing winds strong enough to peel steel from concrete. The bay's currents change direction constantly, making it nearly impossible for construction vessels to hold position. And then came the most dangerous discovery of all. Roughly 50 feet beneath the seabed, engineers found pockets of trapped methane gas, toxic, flammable, and ready to blow if a drill bit hit the wrong spot. Nearly 600 experts spent 9 years just designing this bridge before a single pile went into the water. Over 120 technical studies were completed before construction was even approved. That should tell you everything about how dangerous this site was. When construction finally began, the first problem was the most basic one. How do you anchor anything into a seabed made of mush? The answer was steel. Engineers chose steel piles over concrete, specifically because steel resists saltwater corrosion far better in tidal environments this violent. The piles ranged from 70 to nearly 90 feet tall, each one hammered deep into the sediment until it reached layers stable enough to hold. A specialized spiral welding method was developed just for this project to manufacture piles strong enough to survive the bay's forces. The methane had to be dealt with before any drilling could begin. Steel pipes were inserted into the seabed to slowly release the gas over 6 months, a painstaking process that couldn't be rushed without risking an explosion on the construction site. Because conditions in the bay were so hostile, engineers couldn't build most of the bridge on site. Instead, they went with the same modular approach that worked at Poyang, but at a much larger scale. Foundations, piers, and massive box girders were prefabricated on land, loaded onto barges, and floated out to the construction zone. Giant floating cranes, one weighing over 3,000 tons, anchored themselves in the shifting currents and lifted each piece into place. Every operation was dictated by weather windows. If conditions turned, work stopped. There was no forcing it. The finished bridge stretches 22 miles across the bay, carrying 6 lanes of highway. It's built to survive earthquakes, registering 7 on the Richter scale, and winds that would flatten most structures. And right in the middle of this 22-mile crossing, surrounded by nothing but open water, you'll find a rest stop. A full-service platform built on an artificial island where you can refuel, eat, and look out over the bay from an observation tower nearly 500 feet tall. It exists because the crossing is so long that drivers need a break halfway through, and maintenance crews need a staging area that doesn't require a boat ride from shore. The Hangzhou Bay Bridge took 4 years to build across what its own chief engineer described as the most complicated sea environment in the world. It opened to traffic in 2008, and every day, tens of thousands of vehicles cross a body of water that tried everything in its power to make sure this bridge was never built. And yet, even after conquering the worst bay in China, engineers were about to face something bigger, a crossing so massive it would require more than 5,000 pillars just to hold it up. Bridge #2, Jiaozhou Bay Bridge. By now, you've seen China build across rivers, lakes, and open sea, but the Jiaozhou Bay Bridge is where sheer scale becomes the story. This bridge stretches over 26 miles across Jiaozhou Bay, near the city of Qingdao, and when it opened in 2011, it held the Guinness World Record for the longest bridge over water on Earth. To hold it up, engineers sank more than 5,000 concrete piles into the seabed. The structure consumed 450,000 tons of steel and over 2 million cubic yards of concrete. 10,000 workers built it in just 4 years. But length wasn't the real challenge. Jiaozhou Bay threw problems at this bridge that no other crossing on this list had to face all at the same time. In the winter, sea ice forms across the bay. Floating ice sheets slam into bridge pylons with enormous lateral force, and if those pylons aren't designed to handle it, the ice wins. Engineers shape the pylon bases to deflect and break incoming ice rather than absorb the impact head-on, turning every support column into a blunt icebreaker. And the ice was only part of it. This region of China is earthquake-prone, and you can't build a 26-mile bridge rigid it would snap. Every element was engineered to flex and absorb seismic energy. Isolation bearings at the base of pylons allow controlled movement. Expansion joints between sections let the bridge stretch and compress without cracking. The entire structure was designed to survive a magnitude 8 earthquake and keep standing. Then came the construction challenge that could have derailed the whole project. The bridge was built simultaneously from multiple starting points, separate teams working inward from different sections of the bay, each one building toward the others, across miles of open water. When those segments finally met, they had to align with precision across miles of independently built structure. One miscalculation, one foundation that settled unevenly, and the sections wouldn't connect. They connected. But even a 26-mile bridge across an icy, earthquake-prone bay doesn't prepare you for what came next, because China's most ambitious water crossing isn't just a bridge. It's a bridge, a tunnel, and 4 artificial islands that didn't exist until engineers built them from the ocean floor up. Bridge Hangzhou Kong-Zhuhai-Macau Bridge. This is it, the structure that justifies the title of this video. The Kong-Zhuhai-Macau Bridge stretches 34 miles across the Pearl River Delta, the longest sea crossing ever built. It connects 3 separate cities across one of the busiest shipping lanes on the planet, and it isn't one type of structure. It's everything. Cable-stayed bridges, a sea viaduct, 4 artificial islands, and a 4-mile immersed tube tunnel sitting on the ocean floor, nearly 160 feet below the surface. A bridge alone couldn't work here. The Pearl River estuary carries some of the heaviest ship traffic in the world, and Hong Kong's airport flight paths demanded low-profile structures in certain zones. So engineers designed something no one had ever attempted at this scale: 2 artificial islands in the middle of open ocean, serving as transition points where you descend from the bridge into a tunnel that runs along the seabed, then resurface on the other side. Building those islands was supposed to take 3 years. The team did it in 7 months. They sank 120 massive steel cylinders, each one 72 feet in diameter and up to 165 feet tall, into the soft seabed using synchronized vibratory hammers. The cylinders formed a wall. The water was pumped out. The island was filled and capped. 2 artificial land masses, each covering over 1 million square feet, created from nothing in the middle of the sea. But the islands were just the beginning. The tunnel itself was assembled from 33 prefabricated concrete sections, each one displacing 80,000 tons. They were built in dry docks on land, sealed, floated into position, sunk to a trench on the ocean floor, and joined together with tolerances measured in fractions of an inch underwater, in currents, at depths where divers can barely work. International standards allow immersed tunnels up to 8 inches of settlement. This one was held to under 4. You don't get a second chance when you're joining 80,000-ton sections on the ocean floor. The whole system was designed to last 120 years. It survived Typhoon Mangkhut during construction gusts over 125 miles per hour without a single structural failure. And it was engineered to withstand a magnitude 8 earthquake, while container ships the size of city blocks pass beneath it. Every technique on this countdown: floating construction, deep water pylons, cable-stayed spans, modular prefabrication, immersed tunnels, artificial islands, converges right here. This isn't just a bridge. It's the answer to every engineering problem water can throw at you, built into a single 34-mile structure across open ocean. China didn't just cross the sea. They turned it into a highway.